What made this case different was not simply where it came from. It was how it behaved. When astronomers first tracked its movement, the calculations were straightforward. Its orbit matched the pattern of an object passing through on a hyperbolic path. Hyperbolic means it does not circle back, it enters, curves slightly due to the sun's gravity, and leaves forever. That part made sense, but small corrections began appearing in the tracking data. Tiny deviations from the predicted path. Not dramatic changes, not sharp turns, just slight accelerations that were not fully explained by gravity alone. But small corrections began appearing in the tracking data. Tiny deviations from the predicted path. Not dramatic changes. Not sharp turns, just slight accelerations that were not fully explained by gravity alone. Normally, when a comet-like body approaches the sun, it warms up, ice on its surface can turn into gas. That gas escapes in jets, creating a gentle push. Think of it like a very small rocket engine powered by sunlight. This process can shift an object's path slightly. It is well known and well studied, so scientists looked for signs of outgassing. They searched for visible plumes. They measured changes in brightness that would suggest material was being released. The results were unclear. There were hints of activity, but not enough to fully match the observed acceleration. The push seemed too smooth. Outgassing usually produces uneven forces. Jets turn on and off as the object rotates. The result is a wobbling effect, small, irregular changes. But the acceleration in 3I Atlas appeared steady over long intervals, smooth, continuous. That raised quiet questions. A few researchers began modeling what would happen if the object had a very low mass compared to its surface area. If something is thin and wide, like a sail, sunlight can push it more efficiently. Solar radiation pressure is weak, but over time, it can create measurable effects, especially on light objects. The numbers suggested that if 3I Atlas were extremely low density, almost like a hollow structure or a thin sheet, the observed acceleration could make more sense. That is where the hidden probe theory began to take shape. Let me be clear, no one in the mainstream scientific community announced that this was an alien spacecraft. That is not how serious research works. What they did say was more careful. They said the object's motion could be consistent with non-gravitational forces that might resemble radiation pressure acting on a light structure. It was a possibility, not a conclusion. The deeper analysis focused on its brightness changes. As it rotated, the amount of sunlight it reflected toward Earth varied. This created a light curve, a graph of brightness over time. For most asteroids and comets, these curves are irregular, but understandable. They reflect shape and rotation. In this case, the brightness variations were extreme. The object seemed to change brightness by a large factor within short intervals. That suggested a highly elongated or flat shape. Imagine a thin piece of metal tumbling in space. When its flat side faces you, it appears bright. When its edge faces you, it almost disappears. If 3I Atlas had that kind of geometry, it would be unusual, but not impossible. Nature can produce strange shapes through collisions and erosion over billions of years. Yet simulations showed that maintaining such an extreme shape without breaking apart would require material strength beyond what we typically see in icy bodies. If it were rock, the density should be higher. If it were ice, it should show clearer signs of sublimation near the sun. Instead, the data seemed to sit in between categories. At this point, some voices suggested a thought experiment. What if, instead of a natural fragment, the object was an artificial probe designed to drift silently between star systems? Not powered by engines, not steering actively, but simply riding gravitational paths and radiation pressure over immense spans of time. It sounds dramatic, I know, but in science, even bold ideas begin as simple questions. If an advanced civilization wanted to send a probe across interstellar space, it would face a problem of energy. Fuel is heavy, engines add complexity. Over light years, even small design flaws become fatal. But a passive probe, something like a durable sail, could travel for millions of years without active propulsion. It would not need to hurry, it would only need to survive. When researchers compared the acceleration profile of 3I Atlas with theoretical light sail models, there were similarities. The magnitude of the acceleration was within the range predicted for a thin object pushed by sunlight at that distance from the sun. However, there were also inconsistencies. The orientation changes did not always match simple sail behavior. If it were a flat sheet, we might expect more predictable tumbling patterns. The hidden probe theory does not rely on dramatic maneuvers. It rests on subtle alignment between motion and physics. If the object were artificial, it would likely be ancient, older than human civilization. Possibly older than our species. It would not send radio messages, it would not flash lights, it would simply pass through, collecting data or existing as a remnant of some long-forgotten project. That is what makes the theory unsettling in a quiet way. It does not imagine invasion, it imagines indifference. To test the natural explanations further, astronomers examined its thermal behavior. As it moved closer to the sun, its surface temperature increased. Infrared measurements provided clues about how heat was absorbed and re-emitted. If the object were metallic or composite rather than rocky, its thermal signature might differ. The readings showed that 3I Atlas did not heat up exactly like a typical comet. It lacked strong gas emission lines that would confirm heavy sublimation. But again, absence of strong evidence is not evidence of absence. It may simply have had a crust that limited gas escape. One of the more careful analyses focused on rotation stability. Over weeks of observation, the rotation period shifted slightly, but not chaotically. A fragile natural fragment, under uneven jet forces, would likely spin up or slow down more erratically. Instead, the change appeared gradual. Could that still be natural? Yes, complex internal mass distribution can create damping effects, but the consistency was noteworthy. There was also the matter of trajectory entry angle. When tracing its path backward, it did not align perfectly with the plane of our solar system. It came in from an angle that suggested a random interstellar origin that supports a natural explanation. Artificial probes might be targeted towards star systems directly. Yet a drifting relic would also follow unpredictable paths after millions of gravitational interactions. The key issue remains probability. Interstellar space is vast beyond imagination. The distance between stars is measured in trillions of kilometers. For any object to pass close enough for detailed observation is rare. The odds of that object also having unusual physical properties adds another layer of improbability. But improbability is not impossibility. As the months passed, more refined data came in. High-resolution spectroscopy looked for chemical fingerprints. Most findings pointed toward common elements, carbon compounds, possibly silicates. Nothing screamed advanced alloy, nothing clearly indicated engineered material. And yet, the low-density estimate persisted. If the object's size was correct, and its brightness matched the observed acceleration, then its mass must be surprisingly small. That is where the debate sharpened. Some argued the size might have been overestimated due to reflectivity assumptions. If it were darker than expected, it could be smaller and denser. Adjust the albedo, the reflectivity, and the numbers shift. Others countered that even with reasonable adjustments, the density remained unusually low. The hidden probe theory gained attention, not because of one dramatic discovery, but because multiple small anomalies pointed in the same direction. Smooth acceleration, extreme brightness variation, uncertain density, limited outgassing evidence. Each piece alone could be natural. Together, they formed a pattern that refused to disappear completely. I have lived long enough to see how science handles patterns like this. First comes excitement, then skepticism, then deep, slow analysis. Most of the time, natural explanations win. They should. Nature is more creative than we expect. But sometimes, anomalies push us to widen our thinking. If 3I Atlas were artificial, even as debris, the implications would be enormous. It would mean that technology has existed elsewhere long enough to scatter artifacts between stars. It would mean we are not the first to send objects beyond our home system. Yet we must also ask a harder question. If it were a probe, why did it not show clearer signs of design? Why no clear signals? Why no obvious structure in imaging data? The simplest answer is resolution. At such distances, even our most powerful telescopes see only a point of light. We infer shape from brightness changes, not direct images. A small object can hide enormous detail at that scale. As it moved away from the sun and earth, our ability to study it declined. Signal strength faded, measurement errors grew. Eventually, it slipped beyond the reach of precise instruments. We are left with datasets and interpretations. The hidden probe theory remains exactly what its name suggests. A theory, not proof, not confirmation. A possibility grounded in physics, but surrounded by uncertainty. What makes it compelling is not sensationalism, it is the quiet consistency of the questions. Why was the acceleration so smooth? Why were the brightness swings so extreme? Why did density estimates remain lower than expected? Science demands patience. It demands that we exhaust ordinary explanations before embracing extraordinary ones. And that process is still ongoing. For now, 3I Atlas continues into the dark, carrying its secrets with it. We cannot chase it, we cannot intercept it, we can only analyze what it left behind in our records. And as I look at those records, I do not see a clear answer, I see a doorway slightly open. The hidden probe theory asks us to imagine that sometimes the universe sends us more than rocks and ice. Sometimes it may send artifacts. Not messages written in words, but objects shaped by purpose. The evidence is not conclusive, the debate is not settled, but the questions remain alive. And perhaps the most unsettling thought is this: if one object like this can pass through quietly, how many others have already done so without us noticing at all? As the last clear measurements of 3I Atlas were recorded, the tone inside research circles changed from active investigation to careful reflection. There were no dramatic announcements, no official statements claiming discovery of alien technology. What remained was quieter, and in some ways more powerful than a headline. It was a collection of unresolved details that refused to fully settle into ordinary categories. The hidden probe theory moved into a second phase. Instead of asking whether the object was artificial, scientists began asking a more disciplined question. If it were artificial, what physical signatures should we expect? And did any of those signatures appear in the data we already had? That shift was important. It moved the discussion away from imagination and toward testable criteria. First, they examined structural stability. An artificial probe designed for interstellar travel would likely need to survive extreme temperature changes, radiation exposure, and micrometeorite impacts over millions of years. That means strong materials, possibly composites, possibly layered structures. When researchers modeled the stress forces experienced during its passage near the Sun, 3I Atlas showed no signs of fragmentation, no visible breakup, no sudden changes in rotation that would suggest cracking. That stability was interesting, but still within the range of some natural rocky bodies. Then came the matter of surface uniformity. Spectroscopy data, which breaks light into its component colors to identify materials, did not reveal exotic metals or unusual alloys. The surface appeared dark, possibly carbon-rich. That aligns with many known asteroids. However, spectroscopy at that distance is limited. Its samples reflected sunlight, not internal composition. A coated or weathered surface could hide deeper layers. Interstellar radiation over long times can darken and alter materials, making artificial structures appear natural. Another angle of investigation focused on rotation control. If 3I Atlas were simply a tumbling rock, its rotation should gradually change due to uneven solar heating. This process, known as the Y-Orp effect, can slowly speed up or slow down spinning bodies over time. The measured changes in rotation were small and smooth. Some researchers suggested that the smoothness hinted at internal mass distribution designed to stabilize motion. Others argued that nature can produce balanced shapes through long erosion processes. To evaluate that, simulations compared random natural fragments with engineered shapes exposed to solar forces. The differences were subtle, not decisive, but in several runs, the observed behavior of 3I Atlas matched slightly better with symmetrical, low-density models than with jagged rocky ones. Still, slightly better is not proof. The most intriguing discussion centered on trajectory origin. When scientists traced its incoming path backward across thousands of years, they estimated its approximate direction of origin within the galaxy. It did not point directly to any nearby star system. Instead, it appeared to come from a region between known stellar neighborhoods. That fact weakened the targeted probe idea. If it were sent intentionally toward our solar system, we might expect alignment with a specific star. But if it were a long-drifting relic, launched millions of years ago, and altered by gravitational interactions along the way, its path could easily appear random by the time it reached us. Interstellar space is not empty. It contains faint gas clouds, weak magnetic fields, and occasional stellar encounters. Over vast timescales, Even slight gravitational nudges can alter direction significantly. The age question also became central. Surface exposure to cosmic rays leaves chemical fingerprints. These fingerprints suggested that 3I Atlas had been traveling through interstellar space for an extremely long time, possibly millions or even billions of years. That supports natural origin, but it does not exclude artificial origin. An ancient probe would carry the same exposure marks. Here is where the discussion deepened beyond physics and entered philosophy. If an advanced civilization had existed somewhere in our galaxy long before humans, could they have launched simple probes in many directions, not targeting specific stars, but seeding the galaxy with observers? Such probes would not need active communication, they would only need to record and perhaps transmit if certain conditions were met. No such transmission was clearly detected from 3I Atlas, no radio bursts, no structured signals confirmed beyond doubt, but if it were dormant or damaged after ages of travel, it might remain silent. Another hypothesis suggested something even more subtle. What if it were not a probe designed to communicate, but a piece of debris from a much larger artificial structure? A fragment of a sail, a broken component from an ancient exploration effort. In that case, its unusual properties would not represent active design, but leftover engineering. To test this, density estimates were recalculated using revised brightness models. Depending on assumptions about reflectivity, the object could be denser than initially thought. That adjustment brought it closer to natural asteroid values. Yet uncertainty margins remained wide. The truth is, measurement at astronomical distances always contains error bars. We do not hold the object in our hands. We infer its nature from faint light and motion against distant stars. As someone who has followed space exploration for decades, I find this uncertainty both frustrating and beautiful. Frustrating because we crave answers. Beautiful because the universe remains larger than our expectations. The hidden probe theory does not claim a cover-up. It does not require secret agencies hiding metal fragments in underground labs. The phrase, "what they don't want you to know," often suggests conspiracy. But in reality, what is not widely known is usually not hidden. It is simply unresolved. Scientists do not suppress evidence of alien probes. If anything, such a discovery would be celebrated, careers would be made, history would be rewritten. The caution, you see, is not fear of truth, it is fear of being wrong. And being wrong in science is costly. So where does that leave us? It leaves us with layered probability. The majority of data still supports a natural interstellar object, a fragment ejected from another star system during planet formation or collision. That explanation requires no new physics, no advanced civilizations, yet a small fraction of the data remains slightly out of alignment with expectations. Smooth acceleration, extreme brightness variation, low estimated density, these do not prove artificial origin, but they prevent complete comfort. As 3I Atlas moved beyond our detection range, final tracking confirmed that its path remained stable. No sudden maneuvers, no course corrections. If it were a probe with active control, it did not reveal it. Perhaps that is the most important detail. If intelligence sent something into our system, it either chose not to interact or it was incapable of doing so. In either case, the message, if there was one, was silence. And silence can mean many things. It can mean emptiness. It can mean patience. It can mean distance, so vast that response times exceed civilizations. The hidden probe theory will likely remain in scientific papers and quiet discussions rather than textbooks. It serves as a reminder that our models are incomplete, that when something does not fit perfectly, we must expand inquiry without abandoning rigor. In the coming decades, better telescopes will scan the skies, larger survey systems will detect more interstellar visitors. With improved resolution, we may one day capture detailed images rather than single points of light. If another object like 3I Atlas passes through, we will be ready with sharper tools. If that next visitor shows similar anomalies, the probability balance will shift. Patterns across multiple cases would be far more persuasive than a single mystery. For now, we stand at the edge of interpretation. I do not tell you that 3I Atlas was a hidden probe. I tell you that it was unusual enough to challenge comfort. It reminds us that our solar system is not isolated. Objects cross the vast dark between stars. Some are surely natural fragments, All of them carry stories from distant systems we may never see directly. Whether this particular visitor was rock, ice, or relic, it forced scientists to ask a bold question in a serious way. Could artifacts drift silently through the galaxy, unnoticed for ages, waiting only for a young civilization with telescopes to glimpse them briefly? We cannot answer that yet, but we can say this with certainty. The universe is old. It has had time beyond measure to experiment with life and technology. If intelligence has ever arisen elsewhere, even once, its creations might still be traveling. And when one of those creations, natural or artificial, passes through our neighborhood, we have only a short window to observe it. 3i Atlas gave us that window. It arrived without warning. It left without explanation. It carried anomalies small enough to debate, but large enough to remember. Perhaps the real significance is not what it was, but what it awakened in us, a readiness to question, a willingness to consider that not every visitor is simple, a reminder that discovery often begins with discomfort. As I reflect on this story, with years of watching humanity reach slowly outward into space, I feel less concerned about whether it was a probe and more curious about what comes next. Because if even one interstellar object can spark this level of analysis and imagination, imagine what a closer pass or a future interception mission could reveal. The final truth about 3i Atlas may remain forever uncertain. But uncertainty is not weakness, it is an invitation. An invitation to build better instruments, to look more carefully, to listen not only for loud signals, but for quiet patterns hidden in motion and light. And perhaps the deeper question is not whether something out there has already sent a probe past us, it is whether we are prepared, scientifically and emotionally, for the day when the evidence is no longer subtle at all.